Just a recap of what we were talking about last time. We discussed this channel coding problem where we are trying to send a string, let's say, of n bits or n symbols, but we were restricting ourselves to bits for now, and trying to encode some message in some space, which is 1 to m. Let's say it could be a uniform element of that space. And the rate is defined by kind of log of the number of messages, which is the entropy of the distribution. They're divided by the number of times we need to use the channel, which is the number of transmissions. And we were working with kind of memory-less channels, which means that each transmission can introduce some noise, but it's independent of what happened before. And everything we are talking about here is also discrete, that we are sending symbols from some finite alphabet. The channel is kind of mapping them possibly to some other finite alphabet. And in particular, we calculated channel capacities for a few examples. And we were trying to sort of show that the channel capacity, which is the maximum mutual information between the input and the output of the channel, can be is also the best rate we can hope for, is the supremum of the set of achievable rates. And we proved an upper bound on the rate using Fano's inequality, and we kind of started the proof of a lower bound on the rate. And the construction was just by picking a bunch of random code words. So today I want to kind of do two things. One, finish the analysis of this random code word or this random code, and then also talk about some explicit constructions which are also kind of very motivated by information theory, which get very close to the capacity for the binary symmetric channel. I mean, these generalize to discrete memoryless channels, but as I said last time, a lot of the ideas are already captured in the binary symmetric channel case. So we'll restrict ourselves to this channel for the entire lecture today. And just to remind you of the code and the encoding and decoding scheme, not necessarily efficient, just some maps which will sort of aimed at recovering the original message. From last time was that first we picked the code words as strings of n bits and m such strings, one for each intended message. Each bit in every string was sampled independently to be 0 or 1 with probability half. And we said that this kind of uses the fact that the distribution achieving the channel capacity for the binary symmetric channel is one where kind of you send 0 or 1 with probability half each. If it was some other distribution, we'd use that to sample every element or every single element of the sequence describing a code word. The encoding was just, we already set up these m code words with m and corresponded them to m messages. So we just send the ith code word for the ith message. The decoding was that basically we want to you get some corrupted sequence y bar, and you want to basically find the closest code word to y bar. We wrote a slightly different decoding scheme, which is a bit easier to analyze and about as good. So here we said that because every bit is corrupted with probability p, you think of this error vector z, which is added. Every bit is 1 with probability p, 0 otherwise. And you expect roughly n times p bits to be corrupted. And so we are going to allow for a budget of maybe n times p plus delta corruptions. And for any given received sequence y bar, we look within a ball of that radius, ball with respect to Hamming distance, so how many bits you need to change. And within that, if we find a code word and it's a unique code word within that ball, then we are absolutely, or well, then we are fairly certain that this is what was transmitted. We'll output that. Otherwise, we'll just kind of throw up our hands and output some garbage, or output all zeros, doesn't matter. We'll just not count that towards the success. Okay. Any questions about the channel model, the code, the or the decoding and coding algorithms? So we proceed. None of this is claimed as efficient, and I'm it won't be, but we are trying to say that at least the rate will get very near the capacity of the channel. And in particular, for any epsilon which is less than 0, we can, which is greater than 0, we can get within epsilon less than the capacity. So we can get very close to the capacity. So the supremum will be equal to the capacity. Okay. And we started analyzing the error for this encoding decoding scheme where the estimator or the output that we gave was not equal to the input or the message that was sent. Kind of using some symmetries and so on, we reduced it to the case where we just analyzing the first message. So the symmetry in the code construction. So now suppose we sent x1 bar and the decoder output, and we got y bar, and so the decoder is trying to sort of figure out which message was actually sent. And we said there are two kinds of errors that can happen. Either the code word which was sent, which is x1 bar, is now too far from y bar, so there was a lot of corruption, more than we expected. And in this case, it won't be within this ball of radius that we are considering. So in this case, our decoder will fail. Or it just so happens that within this ball, there is actually another code word. And this is just a fault of our code construction, that there is some such ball within which two code words ended up, possibly. And so in this case, yeah, for this particular y bar, at least, we are just not going to succeed. So, and I kind of asked you to think about both these probabilities, also analyze them based on what we know about concentration or Sanov's theorem. Any guesses, any suggestions for how to analyze this? Even if you didn't have time to think about it before, you can think about it now. It's not that complicated. Okay, so let's look at instead of looking at this y bar, x bar, and so on, we know that x1 bar was actually sent, and y is nothing but plus some error vector. And this error vector is sampled from a distribution which is kind of 1 with probability p and 0 with probability 1 minus p. So let's give it a name. Actually, let's call it the Bernoulli distribution with probability p. Bernoulli is just a 0-1 random variable, and we're sampling n of them. And this event was that the distance between y bar and x1 bar is large, is the same as saying z bar has a lot of ones, or another way of saying that the type of z bar has the probability that the sort of the empirical number of ones is greater than equal to p plus delta. It's should be about p in expectation, but it's large. So the type of this distribution or the type of the sequence is something which has a lot more ones than you would expect. So any bounds or any suggestions for the probability now? Okay, there is a suggestion for Chernoff. Yeah, and in fact, I mean, we have this sort of fancy Chernoff or Sanov. So what we know is that the probability that if you sample according to some distribution Q, n independent samples, and the probability that the type of z bar belongs to some other set pi is less than equal to, in this case, n plus the number of types. The number of types actually is just n. So n times the KL divergence of the closest distribution in pi with Q. And in fact, this particular specific example of finding the closest distribution, we also checked, maybe not with exactly these parameters, but we will get the KL divergence of a Bernoulli distribution with probability P plus delta, and the divergence with Q, which is a Bernoulli distribution with probability P. Right? So it was actually sampled to be 1 with probability P, 0 with probability 1 minus P, ended up having more ones than expected. Okay, so that's Sanoff's theorem. The notation I'm using is just kind of the divergence of P plus delta, and P is just the Bernoulli distribution with probabilities P plus delta, 1 minus P minus delta, and P1 minus P. And this is the same we used in the homework and also in the lectures sometimes. Any questions about this bound? Okay. Now let's go to the second bound. Again, it's not very different, but let's just calculate it. So first of all, there are excuse me, m different events based on which like it's a summation over m minus 1 terms. So there are m minus 1 different events here. So let's just try to calculate an upper bound on any one of those events. And now, what is the chance that, okay, actually before we do that, let's create another error vector, which is just capturing the distance between y bar and xi bar. Okay. And the probability is over both y bar and xi bar, right? Because we are taking the probability over the construction of the code. So in particular, the code involves the all of the code vectors, and we are only conditioning on the first vector or the first code word x1 bar, but the others are completely free right now. Any guesses for what the distribution of this is? I claim that this is also according to some nice distribution. Okay. By the way, plus or minus doesn't matter. We are doing all of this over f2 or f2 to the n rather. So you can also think of it as plus, because we are working with a finite field of size 2. Any guesses for what the distribution of zi bar is like? You can also just fix y bar and then think about the distribution. The hint is that it won't change. You don't have to worry about both y bar and x bar. All right, so let's look at a simpler problem. Let's say we have one bit y, an arbitrary bit y, which is 0 or 1. And now let's add a random bit x, where x is chosen randomly, 0 with probability half, 1 with probability half. Then no matter what y was, y plus x is 0 with probability half and 1 with probability half. Because whatever y is, x is equal to y or x is the opposite of y with probability half each. That gives you 0 or 1 when you add them. So here this is just the same thing is happening n times. Each bit of xi is sampled independently, xi bar. Y bar you can just think of as some fixed sequence. So for every fixed sequence, this is true that zi bar is just distributed with each bit being 0 or 1 with probability half each. And now we are asking, what is the probability that when you look at such a sequence, then the type of this is such that the probability of one or the number of ones is less than equal to p plus delta. And as before, you can calculate this will come out to be less than equal to n times 2 to the, sorry, I forgot to minus n here also. And now we are sampling with half and we got p plus delta. Move that a little. And then we'll multiply with m, which is the number of events. So the whole probability is less than equal to m times n times 2 to the minus n d of p plus delta. Okay. So let's maybe spend a little more time on this. But so we got that the expectation over the generation of the code word, the probability of error, is less than equal to n times 2 to the minus the divergence p plus delta with p. The divergence of, okay, so here we got the KL divergence of p plus delta with the uniform distribution. And this we also know what it comes out to be. It's this was again also on the first homework, that this is just the log of the number of possibilities minus the entropy, in this case the binary entropy of the distribution, or the entropy of the distribution which has ones or zero with probability p plus delta or 1 minus p minus delta. So the first term doesn't quite matter, like, because it's just one term, it's going down with n. The second term is the interesting one because it has m sitting in front, which is this 2 to the nr. And so in particular, the expected probability of error goes to 0 if r is less than, so as n goes to infinity, the probability goes to 0, as if r is less than 1 minus h2 of p plus delta. This is kind of almost what we wanted to prove. We wanted binary entropy of p, and that would be the capacity of the binary symmetric channel. But delta is arbitrarily small, or we can take delta to be sort of as small as we want. And in particular, we can say it suffices to take, if r is less than 1 minus the binary entropy of p minus epsilon, so, and this epsilon will depend on what is the continuity parameter for the binary entropy function. So as an exercise, and if you compute what it means in terms of n, it roughly comes out that not only does the probability of error goes to 0, the probability of error is small for n which is significantly bigger than some polynomial in 1 over epsilon, in particular 1 over epsilon square. So this shows that A, we can get within an arbitrary epsilon of the so I mean, we'll kind of do this in the reverse, where we want to get epsilon close to the capacity of the channel. So based on epsilon, we will choose delta, and then based on delta, we will get a bound of the expected probabilities of how large n should be, so that the bound goes to 0. And in particular, this tells us A, that you can get arbitrarily close, and B, you can actually get close to it with a code word length, which is just polynomial in 1 over epsilon. So you don't really need super large n. Okay. Is that okay? This is just the proof that we can achieve the capacity, or we can get arbitrarily close to it, and hence the supremum achieves it. Okay. So that's yeah. Was there a question? No? Okay, just stop me later.
I have a question. Can you go to like the previous slide?
Sorry?
Yeah.
Okay, the one before this?
The slide before this.
Okay.
Slide 2.
Yeah, I'm on slide 2.
I can't see it. But yeah, so to me, it seems like this is flipped in the sense that in the first case, we are considering where like x1 is fixed, right? And the distribution of z is like Bernoulli with half, right? So why is it p in the first case?
Okay, good. Good. That's. I mean, we are considering that we did transmit x1 bar, or we are rather looking at the event that we did transmit x1 bar. So we can't, like x1 bar is already transmitted, and we are not thinking about the distribution of that at random. We are just saying what y did to it. Whereas in the second case, we transmitted x1 bar, but the choice of x2 bar or x3 bar, we haven't said anything about, so that we can still choose.
Yes, but then isn't z the random error? So that is with a.
So if I tell you that I transmitted x1 bar, or if I
x we pick with like this px distribution.
Right, but if I tell you that I transmitted x1 bar, at that point, so okay, the better answer, I guess, is that y bar depends on x1. It depends on x1 bar. It's not independent. So y bar doesn't depend on x2 bar at all, because we transmitted x1 bar. X2 bar is just completely independently chosen. And y bar depends on x1 bar. So we can't do this trick of fix y bar and now independently sample x1 bar and see what happens. They have a joint distribution. Does that make sense? So I'm using the fact that y bar depends on x1 bar. And here I'm, so and here I'm using the fact that y bar and x2 bar are independent. So when I'm analyzing the error vector, I can't just say that fix y bar and now sample x1 bar completely uniformly from its distribution as if it was unaffected by fixing y bar. It is not unaffected, it's actually affected because they have a joint distribution. But when I'm talking about x2 bar, I can say this, that fix y bar and now look at the distribution of x2 bar as if it's completely unaffected by the choice of y bar, because it is. Does that make sense? Because I'm conditioning on the event that I sent the first message. So I sent x1 bar and then y bar came out, and now x1 bar and y bar have a joint distribution. But I sent x1 bar and y bar came out, and it has nothing to do with what x2 bar looked like. So x2 bar and y bar are independent.
Right, but but what is the distribution of like y bar given x1 bar? That would just be the distribution of this z, this error z, right?
Yeah, which is Bernoulli with parameter p. The distribution of y bar given x1 bar is very easy to analyze, and because it's a symmetric channel, the distribution of x1 bar given y bar is also the same, and that's just Bernoulli with probability p.
Oh, it should be okay. Okay, my confusion was that. I thought it was Bernoulli with half.
No, here it's p, right?
Okay, sorry.
It is.
Yeah.
Okay.
Yeah. Okay.
All right. Any other questions? Okay. So just maybe revisiting a little bit about what we did. We kind of constructed this random code and just see what it buys us. I mean, the way it's written, of course, rate-wise, it's great. We got as good a rate as we could have hoped for. We got arbitrarily close to capacity. Reliability, I mean, okay, the rest of it is not always is not a formal term, but in some sense, you can show that the random code construction not just works in expectation, but works in high probability. So, I mean, you sample a random code, or sort of, if I sample a random code, probably kind of within my lifetime, I'm not going to see a problem with it. So it's not a bad, kind of okay. It's not such, I mean, like, I don't have a 100% guarantee, but I have 99.999%, and you can put as many nines as you want. So it's not a bad, the problem, the few other things which are problematic. One is storage. So the way I kind of stored this code is just that I kind of actually wrote down these m strings, x1 bar, xm bar. There were these kind of 2 to the n times r strings. So I had to write down an exponential number of strings and just kind of remember this entire code book. And when you wanted to send message m, I kind of went and looked in this entire code book and sent the right message. So it needs a lot of storage to even just kind of remember the code. Okay. Sending the code word is not too complicated. It's just look up in this exponential size table. So but that's still a lot of work. Algorithms for, as I said, encoding is not bad. Decoding, the way I presented the algorithm, kind of just look at this entire ball, which is possibly exponentially many strings, see if you have a code word there or not. So look up this entire ball, then at the same time, keep looking up this exponential size code book and try to match things. It's an algorithm, but kind of no one should ever run it. So it's a horribly slow algorithm, exponential time in particular. And moreover, the last point is quite vague, but different, as I said, like coding theory is also, the codes are also used as kind of just mathematical abstractions for other settings. And because it's a random code, it might not capture whatever structure we are trying to use in our application. So if you want to use this code as a mathematical object, it might not carry interesting properties for us. So it's often interesting to look for codes with various different properties for different applications. And we may see some examples. So, but at least for the first two, it's kind of clear that it needs a lot of storage, and at least the algorithm we described was not very good. And for this kind of setup, we don't believe there are any good algorithms. I mean, we don't quite know how to prove p is not equal to np, but we don't really think there are good algorithms for this sort of thing. Okay. We can at least partially resolve some of the issues with what are called linear codes. So recall that this set of two elements F2 is 0, 1, which I've been using sort of as a field. So in particular, you can add two things or multiply two things. It's not so something very involved. You're just having zeros and ones, so there's not too many possibilities. But you add or multiply modulo 2. In general, for a prime p, you can add multiply modulo p. You can also define things for prime powers, but we'll not need it. And now, a linear code, instead of just a subset of, let's say, f2 to the n, let's say, we are actually looking at a subspace. So a linear code is a subspace of a vector space over a finite field, or so f2 to the n for the rest of this lecture anyway. So a linear code is a subspace of f2 to the n. Okay. And moreover, you can write down a basis for this subspace. So you can represent it in the following way, that let's say if it's a k-dimensional subspace. So so I will use this symbol C for both kind of the map, which does the encoding, and also just the set of all code words or the subspace itself. I'll just call the subspace C. And dimension of this subspace is K, and you can also write it this way, that you sort of write down the basis elements for the subspace in the as columns of a matrix G, and then you can just say that this subspace is the image of G. Well, because you wrote down all the basis elements as columns. Okay. So there is in particular a matrix G, which has this property that you multiply some W, which is a k-bit string to it, and you get an outcome which is an n-bit string, which is one of your code words or some element in your code book. And every element of your subspace or code book can be generated this way. Is that okay? I mean, yeah, here I'm not using anything about it's a code. I'm just saying that's what a subspace is. You can look at a basis for a subspace and put them in columns of a matrix. But then the nice thing is, storage is very easy, because I don't need to store the entire code book. I just store this matrix. Okay. I can just store G, which is called the generator matrix of the code. So and there's nothing very subtle about the name. It generates every code word. Encoding is still very easy. It's a matrix vector multiplication. So you get your you want to encode the message W, just multiply W as a vector with this matrix G, and out comes the code word. Notice that I kind of dropped this notation of bar for code words. I'm not calling them sort of W bar or X bar or anything, just because we will talk about vectors only for the next few lectures. So it will just get a little cumbersome to always talk with the bar notation. But if something gets confusing, let me know. And the decoding, of course, is still is something which requires work. Decoding as in you sent a message, there was an error in the channel, but suppose I told you that there was no error. Okay, so sort of I gave you X, which I promised is a code word. So can you find W such that G times W is equal to X? Okay. So given a code word, can you find the message from which it came? Not given a noisy, corrupted code word, nothing, just given an actual code word. Any guesses how?
You do the inverse.
Yeah, so I mean, G is not necessarily an invertible matrix, it's rectangular. But you can basically invert it because it's an overdetermined system. So you have, if you look at GW equals X, you have n equations or n rows and k variables, and you know that there is a solution. So if there is a solution, you can find it, and we will only try to construct sort of things where there is a unique solution. Otherwise, this will not be a good code. But so you can directly find it using Gaussian elimination. You just have a bunch of equations. You want to find a solution to these linear equations. Or you can sort of find G star such that for every valid code word, if you look at G star X and then you multiply by G, you get X. So then G star X is your W. Okay. So why is that? Because you know that there is a solution. So G is a rectangular matrix, but you just kind of write down G. It has n rows, k columns. You just pick k linearly independent rows and just invert that. So if you know that there is a solution, it must satisfy all equations. In particular, it must satisfy these k equations. But if that gives you a unique solution, that must be a solution to everything else. So just invert this part. Okay. So select k linearly independent columns and then invert. Even if that doesn't make sense, don't worry about it. All I'm just trying to say is that there is a polynomial time way to do this. So by easy, I just mean polynomial time for now. For specific codes, we might also worry about how long it takes as a function of n, whether that polynomial is n square or n cube or n log n or n. And that I'm not saying is automatic, but for this lecture, I'll only worry about polynomial time. Any questions about this? So then for this lecture, we'll kind of reset our goal a little bit. I mean, we'll also change it multiple times, but so given X that was sent over the channel, you kind of received Y. And now the task of noisy decoding, instead of saying that given Y, find me W, I can just say given Y, find me X, because the rest is easy. Okay. So the task of noisy decoding can also be changed a little. So given Y, find X. Okay. Y is noisy. That is not easy. That's not necessarily easy. That's the whole game. And rate-wise, these codes are good. You can show that random linear codes also achieve capacity, like we argued for random codes, although the argument is a little more involved. We'll not necessarily go through it. But so these codes are not bad. They pretty much have all the nice properties we have seen so far. At the same time, they have a lot of additional structure, which is nice. Any questions before we proceed? And we can always just kind of restrict ourselves to given a noisy sort of code word or sort of code word plus noise, just find me the code word. Don't worry about finding the message. I can find that myself. Right. There is another matrix which is associated with a code called the parity check matrix. And I apologize that H conflicts with the entropy symbol, but H is the standard one for parity check matrices, so I'll keep it. And this is just using the fact that if G is a generator matrix, then the dimension of the image of G, as we said, is K. So I can find a matrix with n minus k rows such that the kernel of this matrix is the image of G, because the kernel of a matrix with n minus k, let's say linearly independent rows, is k dimensional. So in particular, I can construct one which has the kernel as the as image of G or as the code. So our code now, instead of being the image of G, can also be thought of as the kernel of H. Okay. And this has a nice property that, I mean, as the name suggests, instead of maybe constructing or like encoding a message, if I gave you a code word and you wanted to just quickly check if it's a code word or not, if it's valid or not, that's very easy. Just multiply it with h, see if you get 0. The code is equal to the kernel, so something is in the code if and only if h times x is 0, right? So c is equal to the set of all strings. So that's a very easy way to check if something is a valid code word. And if you sort of ever sort of downloaded something over a slow internet connection from some of these old websites, they will say computing parity checksum towards the end, or sometimes if there is corruption, the parity checksum will fail. This is what's going on there. You can basically check quickly if you're downloading or getting a valid encoding of something or not. And as an example, consider this specific code where if you notice, the columns are just the numbers 1 to 7 written in binary. So I have 001, 010, and so on. And I claim that you can define a code which is the kernel of this matrix, of course, which is a set of 7-bit strings. What's the dimension of C? Four. Good. So, and I claim that it can actually fix any 1-bit error. So let's say EI is, so they're giving 7-bit strings, which are code words. And let's say you make an error in one of these positions. So you have EI, which is just kind of 1 in one of the 7 positions. Then if you receive such a y, then h times y is equal to h times x plus h times EI. This is 0 by assumption. So you get h times EI. And what is h times EI? It is just actually equal to a column whose contents are I in binary. So you multiply it with this corrupted code word, or this corrupted y that you received with the matrix H, and it actually tells you exactly the location of the position where the error happened, and you can decode it. So this can actually decode 1 bit of error in the adversarial or worst case model. 1 bit could be anywhere. And this is called the Hamming code in particular. And we'll talk more about worst case errors next week, but this is just an example of a parity check matrix. Okay, any questions before we proceed? All right, let me, I want to kind of give an overview of one construction of codes which gets close to capacity, and in particular, you can get low probability of error. So you can, for binary symmetric channel, the capacity is 1 minus the binary entropy of P, and you can get epsilon close to it and have low probability of error for n, which is greater than equal to some polynomial in 1 over epsilon. Not necessarily the exponent 2, but some bounded exponent of 1 over epsilon. And I mean, there are other ways of getting close to capacity in explicit way, but they require potentially n, which is much larger as a function of epsilon, maybe exponential, or if the running time is exponential in epsilon. These codes achieve a running time which is a polynomial in n and polynomial in 1 over epsilon, and have a completely explicit description. In fact, they also have very nice encoding and decoding algorithms. So you can decode and encode them in order n log n time. We won't necessarily discuss the very fast encoding decoding algorithms. Just observe that you can do that in polynomial time. But the code construction itself is very nice and explicit, and this is due to Arikan from 2009. There are improvements to these since then. This is a whole area, and this can be applied more generally to discrete memoryless channels. And even for binary symmetric channels, there's like very recent work from last year, which by Guruswamy et al., which achieves an exponent arbitrarily close to 2 for epsilon. So instead of this C, you get 2.0001 or sort of however close to 2 you want. I just will kind of overview Arikan's original construction. Even there, we'll not go through the full analysis. Okay, going back, recall that our goal is to find the code word that we started with. So the X is a code word. You tried to transmit that. The error happened, which is Z, and the Z is distributed according to the Bernoulli distribution. And we just want to find X now. So from X, we will recover that W that we wanted ourselves, that we are not going to talk about. Okay. And let's say we want this probability to go to 0, sort of as n goes to infinity at least, and we'll see more about the form of this probability. Any questions about the task we want to do? And again, we want to be close to capacity, so the dimension of the space of codes, which is K, should be large. So we want it to be arbitrarily close to the capacity. Okay. And the way we will kind of achieve this is by going through an intermediate task, which we'll call linear compression. So this is sort of, here we'll think just of the error vector for a bit. Let's say you have Z, which is distributed according to the Bernoulli distribution. And you want to, instead of sending n bits, or instead of kind of, so this is the error vector. There's no further error. Okay, we are just hypothetically as an as an exercise trying to think about compressing Z. Okay, and the goal is to compress it so that we can later uncompress it back and recover the original message, at least with high probability over all Z's, okay? Or the original vector, the error vector, high probability over all Z's. So first question is, how small can M be if we want to compress n bits to m bits? How small can we hope for M to be, or how good a compression can we hope for? See, there is a question in chat about the parity check matrix. If there is a simple formula for G from H. Not that I know of. So it's a question about if you have the basis vectors for a generic subspace in F2 to the n, is there a direct formula for the subspace which is kind of I don't want to use the word orthogonal, but which has kind of dot product 0 for all vectors in your original subspace. And that's, yeah, there is no simple recipe directly for all subspaces. I mean, you can compute it in polynomial time, but I don't know of a single closed form expression. All right. Going back to this example, I want to know how small can we hope to make M, or sort of okay, for some reason it's not refreshing. Sorry. Okay, so this is something, yeah, so we can't compress smaller than the entropy. We already saw in the first lecture that if you're trying to send something and you're trying to compress it, entropy is a lower bound. So M should be I mean, if you're trying to recover it with probability, which is a probability of error, which is 0, then M should be at least the entropy of the message we sent. If the error probability is 0, well, actually, even if it's going to 0, sorry. And the entropy of Z is n times the binary entropy of P. So we can't hope for M to be much smaller than the binary entropy of P. So let's say we kind of set our tasks to, we don't want it to be much larger. So we'll allow an epsilon slack, but that's about it. Now, my claim is that if I didn't if I just wanted to solve this compression problem, this is actually easy. So you just want to compress n bits to m bits. You know that the n bits are sort of distributed according to the Bernoulli distribution, and you want to be able to recover. That's I'll leave it to you as an exercise to think why that is easy. This is just compression, and I haven't used the part linear yet. So the interesting aspect of the problem is that I want to compress it in a linear way. So I'll use again this symbol H for this matrix. So I don't just want to compress, I want to compress by multiplying with a matrix. So in a very special way, I want to compress. So I want to find a matrix H, which is M cross N, such that the compression should always look like H times Z. Decompression can still be whatever you want. And my claim is that if you can solve the compression problem, then you can also solve the problem of constructing the code. Because you just take this matrix to be the parity check matrix of a code, and that will actually be a code very close to capacity in general. So let's check that. But is the claim okay? Just a statement, or just what the question of linear compression is? All right, so let's check that. So because I've told you what the code is, given H, you can find some matrix G, which is the generator matrix of the code, and you can kind of sort of figure out how to do encoding yourself. So encoding for a code which is a subspace is easy. You just figure out a basis for that subspace. The question is decoding. Okay. And now I have a code word X in this code. And when I sent to you, you received, let's say, X plus Z. And you wanted to decode this received word. And my claim is the parity check matrix, or like this sort of compression combined with parity check, can actually do what we saw in the Hamming code example. It can tell you exactly what the error is. So here's how the decoding algorithm works. So the decoding of, let's call this Y. The decoding of Y is nothing but the decompression algorithm applied to H of Y plus Y. Okay. Why is this? Because H of Y is equal to H of, H times, sorry, got used to saying H of, H times X plus H times Z. This is 0 by definition, H times X, because X is a code word. H times Z is a compression. So then with high probability over the choice of Z, the decompression of H times Z is equal to Z. And If that is indeed the case, then you will get, if you succeed in decompressing it correctly, then you will get uh, z plus y, which is actually x plus z, and you will recover x. So nothing deep. As in the Hamming code, we saw that you multiply with the parity check matrix, and you can read off the error, the position of the error, or it tells you where the error is. In this case, you multiply with the parity check matrix, and combined with the decompression, it tells you what the error is exactly, the error vector. Once you get the error vector, you just kind of add it back again, fix it. So that's why linear compression gives us codes. And moreover, it gives a good code in the sense that the rate is good. So the dimension of the subspace of is n minus m, because m was the dimension of, or the number of rows in the parity check matrix, and n minus m is greater than equal to n times 1 minus the binary entropy of P minus epsilon, because we are taking m to be less than equal to the binary entropy of P plus epsilon times n. So if we have good linear compression, then we have the kind of code we want. Okay. Any questions? All right, so the linearity in linear compression really helps us create this kind of code. And so now let's just talk about constructing a good linear compression scheme. The next observation is that linear compression scheme can be viewed in a slightly different way, which I'll call entropy polarization. And I mean, it implies some kind of entropy polarization, but we'll be much more interested in the reverse connection, that some sort of polarization will give us a linear compression scheme, which is what we want anyway. So before going there, let's just try to observe what I mean by entropy polarization, and we'll define it precisely in a minute. But my claim is that H is a matrix with m rows. Just add n minus m additional rows at the bottom, which are linearly independent, and so the whole thing is invertible. So let's create this matrix P, which is H combined with some extra sort of filler rows, so that it becomes a square matrix and an invertible one. And now let's try to understand what happens when we multiply vector z with this square matrix P. Okay, I'm calling this W again. This has nothing to do with the messages. Ignore that for now. Just let's call this output W. And now my question is, what does the entropy of W look like? And what does the entropy in each bit of W look like? Okay. So first, what is the entropy of W? My claim is that this is equal to the entropy of Z, because it's an invertible matrix. If you give me W, I can reconstruct Z. And so there is a bijective correspondence between the two distributions. Another way of saying it is that the entropy of W and Z is equal to the entropy of W, or it's also equal to the entropy of Z, because given one, the entropy of the other is 0. So, and this is n times the binary entropy of P. And now I claim that if I had the first m rows which formed a good compression scheme, then the entropy in the remaining rows after m is basically negligible. So these are last n minus m bits of W. And the entropy in these is negligible, conditioned on the values in the first m rows, okay? As conditioned again in the average sense, the random variable, etc. This notation just means W1 to Wm. We've been using it occasionally when we were writing more complicated conditioning expressions, and we'll need it today. So this is just W1 to Wm. And think of delta going to 0. So my claim is that if the error probability of your decompression scheme is at most delta, then you can bound the entropy in the remaining n minus m entries of W after kind of corresponding to this sort of filler matrix H prime as something very, very small, in particular if delta is going to 0, or think of even delta smaller than 1 over n if you like, and then this quantity is basically a constant. And we are talking about lots of entries. So on average, every independent single entry has no entropy. You can check this as the expression suggests. You can use Fano's inequality to do this, so try it out. Okay. I'm more interested in the opposite direction, which is saying that if you have a matrix which has this property that in some places there is lots of entropy and the rest of the matrix has kind of 0 entropy, the rest of the entries have 0 entropy or very small, then that forms a good linear compression scheme. So let's define that a little more precisely. So suppose we take any invertible square matrix. Now it's not coming in this way. You kind of have H prime stacked or something. It's just an arbitrary matrix. Okay, and we are going to try and construct an H or a compression scheme out of it. So right now this is just an arbitrary P. We will call it epsilon tau polarizing if it has this property that the number of coordinates where kind of conditioned on the previous stuff, the entropy of that coordinate is bigger than tau. The number of such coordinates is precisely what we would have had in a linear compression scheme. So the number of such coordinates is roughly binary entropy of P times n plus an epsilon again for slack. And all the other coordinates, again, conditioned on stuff before them, have entropy which is very small. These are not necessarily the first few coordinates. These are somewhere in among the n coordinates, but there are some, the set of such coordinates is small. Again, as an exercise, you can check that the set of such coordinates cannot be too small because, well, Z has some entropy. So, we are actually saying that compression matrices or like this polarization, like a polarizing matrix is one where this set is about as small as we can hope for. And if we can construct such a matrix, I'll claim that we can find the linear compression scheme. Any questions about the definition of polarizing matrix? Okay, so intuitively, it should look like this. There will be a bunch of coordinates which will have a lot of entropy. I mean, here, by the way, because we have about H2 of P plus epsilon times n coordinates, and almost all the entropy is contained here, which means that each of these terms must be relatively close to 1. So the first few coordinates in this setup must have entropy very close to 1, and the last few coordinates will have entropy very close to 0. And we are basically defining a polarizing matrix as something with such a property, that the outcome is such that in some positions, the entropy conditioned on the stuff before it is very close to 1, and some other positions it's close to 0. We are only just saying that for the right number of coordinates is close to 0, just an averaging argument will imply that the rest must be close to 1. So that's why it's called polarizing. If you just look at Z itself, the entropy of every position is binary entropy of P, even conditioned on previous stuff, because all positions are independent. So each entry of Z has the same entropy. Now you multiply it with this matrix P, and now some positions have a lot of entropy, some positions have basically 0 entropy, and so that's intuitively a compression scheme because we only should care about the positions with a lot of entropy, and let's make this precise. So my claim is that if you have a polarizing invertible matrix, then you have a compression scheme. And the compression scheme is just that you multiply Z with your matrix, but ignore all coordinates outside this set S tau and just throw them away and just only return the coordinates in S tau. Another way of saying is just P sub S tau times C, where kind of you just kind of delete all rows which are so that's at least something which gives me an output with the right dimension, because the size of S tau is about correct. It's an epsilon tau polarizing matrix. So the size of S tau, as we said, is less than equal to the binary entropy of P plus epsilon times N. So the output of the compressor is about the right size. The fact that you can decompress it requires work, but the decompression is not too involved. So we'll do it in two steps. We'll first try to, like, without deleting these entries, we would have had some W with Z, sort of W is equal to P times Z, if P was the entire square matrix. So we'll try to find this entire W and then just multiply by P inverse. And instead of finding W as usual, we'll kind of construct an estimator, which will be our best guess for W. And then we'll just try to look at what is the probability that we make a mistake in constructing W correctly. If we construct W correctly, then P inverse is known. We can just multiply by it. And the decompressing algorithm is, again, relatively simple. Just go in order. For every entry, if this entry is in S tau, then yeah, you already know what the value should be. It's just whatever is written as Y. Right? Because in the compression scheme, we just kind of delete a bunch of entries from W. So if this is one of the non-deleted entries, then you should just use it. And if it's one of the entries that was deleted, just take your best guess based on what came before it. So the entries before it in your estimate W hat so far, just condition on them and calculate the value which will maximize, which kind of has the largest probability. Is the decompression algorithm okay? Yes, no? I lost you 10 minutes ago. So one of those, hopefully not. I can also go back to 2 slides ago if something was lost. Sorry, so what you were saying?
Can I ask a question? So how important is this maximization step? Can I just put in garbage for all coordinates that are not in S tau?
No, you can't put garbage because there are 2 reasons. One, we are going to reconstruct the entire Z, which is an n-bit string. If you put garbage in even like 0.1 times n bits in W hat, the bits of Z will be, there are some linear combinations of bits of W hat. So they will just be completely nonsense. If you put garbage,
so I can't even get a bound on it saying it's close to the correct Z?
Sorry? Well, I mean, if you kind of guess with some, so if you kind of take a vector and mess up 0.1 fraction of the bits, but then multiply it by some sort of completely arbitrary matrix, and we are not necessarily using features of P inverse right now. So if you, in principle, if you multiply by an arbitrary matrix, the new thing could have very bad entries in terms of what it looks like, or you could, and so here we are talking about 1 minus h2 of P fraction of the bits of W hat. And if you put garbage in that many bits, it could really mess up W completely. You can say that instead of this maximum number, you will kind of put B equals 0 with some probability, B equals 1 with some probability, which is whatever is this probability of W hat coming out. And then, yeah, we can say how close is the resulting Z, or we can get some estimates on that. But if you are putting complete random garbage and not using the information that you have about the distribution of B, then it can be very bad.
Okay, thank you.
Yeah, you could replace this argmax step by saying that you sample according to this distribution, but then you have to analyze a little bit of how P inverse looks like. And I don't know exactly, but I can suspect that you might get something based, particularly if the bounds are very strong. But these probabilities are problematic, as I guess maybe you already were suspecting. It's not clear how to compute them. And like in particular, I've not told you how to sort of compute on what came before and so on. You can do this in polynomial time, and that's not so bad. You can see that you can keep a running tally of this. Not necessarily much faster. I claimed n log n decoding. For the actual n log n decoding, you need something more involved, and I'm not going to discuss that. But at least this is just abstractly for any kind of polarizing matrix. I'm saying that you can build this compression decompression. Now, the analysis of this I will actually give you as an exercise. So I'll say that if you had an epsilon tau polarizing matrix, which means the set S tau was defined for entropies which were greater than tau, then the probability that you kind of calculate W hat incorrectly is at most n times tau. And we can think of tau as kind of arbitrarily small. So you can think of tau as little o of 1 over n. So this probability of error will still be going to 0. And in particular, we'll be able to construct, or I'll just claim epsilon tau polarizing matrices which have very, very small tau, or you can get it to be very small if you want. Any questions about the algorithm? The analysis I will leave as an exercise, but ask me if something is not clear. I claim that if you break it into these two pieces, it shouldn't be too bad. All right. So now let's come to the kind of final task of actually constructing a polarizing matrix. And this comes from this very nice observation about kind of a vector of size 2. So let's say you have Z1, Z2, both independent Bernoulli random variables. And you construct W1, W2 by just kind of saying, you sort of look at Z1 plus Z2 in the first coordinate and Z2 in the second coordinate. And my claim is that the entropy already slightly polarizes. The entropy of the first coordinate is now slightly more than the entropy in the second coordinate. In Z1, Z2, both coordinates had equal entropy, even if you conditioned the second one on the first one. Okay, so any guesses on what the entropy of W1 is, or what the entropy of W2 conditioned on W1 is? You can start with the first one if you like. So the W1 is still a Bernoulli random variable. It's either 0 or 1. It's Z1 plus Z2, right? There is no conditioning, nothing. We just want to analyze what is the probability that it's 1. Okay. And what is the probability that it's 1? You are adding Z1 plus Z2. Adding, again, modulo 2, so it's an XOR, or kind of, you want to look at what's the chance that Z1 and Z2 are different. So Z1 and Z2 are different if either Z1 is 1 and Z2 is 0, or the other way around. And let's say P is less than half, because error rate less than half is the interesting case anyway. If error rate is more than half, we can just sort of complement everything. Then I claim that 2P times 1 minus P is greater than P. Or in other words, 1 minus P is greater than half, which is true if P is less than half. So, and the binary entropy function is increasing, so is an increasing function. So this is actually greater than the entropy you had in the first coordinate of. And by joint entropy, you can look at entropy of W2 given W1 is the entropy of W1, W2 minus the entropy of W1, which is 2 times the binary entropy of P minus. So the total entropy remains the same because the matrix is invertible. If I give you both W1, W2, you can find Z1, Z2. So the conditional entropy of the second coordinate condition on the first one reduced a bit, and the entropy of the first coordinate increased a bit. And so you kind of at least had this slight polarization, sort of not both coordinates were no longer equal, they went up or down a little bit. And the final matrix we'll construct is basically recursing on this. So before we go there, I just want to write this in terms of this picture. So you think of a circuit where you kind of take Z2 and add it to Z1, and kind of that's the blue output wire. And then the green wire is where you just kind of send W2 by itself, or so Z2 by itself, and that's your W2. Is the calculation for this size 2 matrix okay? And also this pictorial representation? Will we proceed? And then the general case is basically a recursion of this. So instead of doing this once, you do this multiple times at different levels. So you can think of either P sub n as applying whatever polarization you have to n over 2 bits, and then kind of thinking of these as big vectors and applying this operation again to these vectors. And so you can write it in this way. As an exercise or understanding the structure, it's good to check that you can compute W equals P times Z in time order n log n. That's again using the recursive structure of the matrix. It's nothing too involved, but it's a good way to think about the recursive structure. Pictorially, you can represent it in this way that maybe you go in steps. So first, you kind of just applied this sort of 2-bit matrix on Z1 and Zn over 2 plus 1, Z2 and Zn over 2 plus 2, and so on. Once you got the outputs of these, you applied this, again, this 2-bit operation, but now on things which were n over 4 apart. So Z1 and Zn over 4 plus 1, Z2, Zn over 4 plus 2, and so on. Then you again did the same thing, but now kind of things which were n over 8 apart. This is just another way of writing the recursive of this. So this is just an explicit representation of the matrix. And well, one way of solving the exercise is that just counting that the complexity or the amount of time you need to calculate this is just the number of plus things that appear in this diagram, and the number of plus things in the diagram you can calculate directly. Okay. So is this diagram or the description of this matrix okay? So the matrix is now explicit. We have completely written down a matrix. I'll claim that this is polarizing. I'll not give the proof in detail, but is the description of the matrix okay? It's a completely explicit matrix. You can multiply it with very fast, and that gives you, if it's polarizing, that will give you a compression scheme, and we know that a compression scheme will give you a code. And the way it's analyzed is a bit involved. So it will take about a lecture of martingale analysis. I'll not get into the details of that, but roughly the way you analyze it is you kind of follow one row in this diagram. So you select a random I, and then you define a variable x sub j, which is the entropy of the position written at that I, or conditioned on the stuff before it. And you kind of don't know I. So you want to see what xj plus 1 looks like given the value of xj, but not necessarily knowing I. Because if you know I, then everything is kind of deterministic. There is no other probability. Right? So say I selected an I didn't tell you what I was. I just told you what x1 was. Now can you guess what x2 will be like? Then if you know x2, will you be able to guess what x3 will be like, and so on. And another way to think about it is that if you didn't know I, you started and all rows had a probability which was H2 of P. And now, after one step of this process, some rows have even conditioned on their previous stuff. The entropy is H2 of 2P times 1 minus P. And for other rows, it's 2H2 of P minus that quantity. So with probability half, it went up. With probability half, it went down for the value. And you can analyze this sort of as you progress in this diagram. There are t steps where t is equal to log n. And you can prove a theorem about the speed of polarization, which says that the speed the value of xt sort of gets close to 0 or 1 exponentially fast, or rather that the fact that it's not close to 0 or 1, or it's not within gamma t of 0 or gamma to the t of 1, the probability of that becomes very small. So in particular, if you take gamma to be 1/4, it tells you that you are within tau of either 0 or 1, the probability of that is very small. And you can even take tau to be, as in this example, 1 over n squared. So that's roughly the construction. Yeah, I'll not necessarily get into the details of this construction, but we can discuss it in office hours if you are interested. I mean, I'll have to look some things up. I don't necessarily remember. It's a bit of a messy calculation. But yeah, okay, let me stop there. Let me just say that like the more advanced analyses, instead of just saying that you always multiply with the same kind of 2 by 2 matrix in every step of this diagram, you choose a fresh matrix for every step of this diagram and which row you are at. So you kind of get this binary tree in terms of how your entropies look in different rows. And at every node of this binary tree, you get to pick a like fresh, small, maybe 2 by 2 matrix or k by k matrix with which you are multiplying. And there is some way of kind of picking these matrices so that your speed of polarization is very fast, and you can even get away with n, which is about 1 over epsilon square when you're epsilon close to capacity. That's kind of all I'll say about these codes. Next week, we'll start talking about the Hamming model or worst case errors. If you have any questions, we can discuss.